method, right? There are two methods in which they do it. One is single-ended. Okay, single-end means you give only one input and you have the output across the terminal, right? So this would be the output signal with respect to time. Okay, and then the second method of operation in which your differential amplifier works is your differential input. Uh, you can make a common CM level is common mode level. Okay, common mode level. You can give the input, and you have the elements of node, whatever be the node you need to analyze, with an impedance of ZS, and your output is taken at the differential point. So you get differential signals. So always remember, if this is the positive part of the signal, then on the difference end, it should be the negative part at the same instant of time. Okay. And if it is negative, then it should be the positive part in the other end. Okay. That's why it is differential, right? So this is how the operation of single-ended and differential signal is expressed, right? Now there are advantages. We have already seen what is the advantages in the last class, but just to figuratively plot it out, what are the major advantages? It reduces the coupling effect. Okay, so coupling is between two elements you need to join, and the effect of reduction is done. Okay, which means with respect to the signals. Okay, and then the other advantage is common mode rejection occurs, and with respect to the supply noise. Okay, the noise factor in the supply is being rejected by this CM mode. Okay, so these are two major advantages of differential operations. Now we'll see a very simple differential circuit. This is two uh, differential transistors with M1 and M2, right? And then you have the normal common source. You This is symmetry. Okay, symmetry means when you cut it across this end, you exactly have the same elements, right, on the left and the right. So it's a symmetric circuit. So when you take this V out one, it is very similar to a common source amplifier, right? Input, output with a resistive load, right? So this point X is the point of node of analysis. And then similarly on the left hand side with input V2, you have output as V out is the another common source amplifier who's given the output V out, right? So when you represent with respect to time, this is the common mode input, and this is the differential signal V1, and this is the input V2. Okay. When you look at input V1 and V2, they have this portion is for the V1 signal, okay, where your input is represented with respect to the V in value, that is this particular point. Okay. And then the next input is with respect to V2, that is from this particular point. Okay. And the input signal is given over here. This is the input signal. Okay. Now these two signals are given in such a fashion that they are a differential signal. Last class we saw what is the properties of a differential signal and how is to be it to be represented, right? So when you give a differential input with the CM mode, common mode, then you get an output. Okay, so your out is what is depicted at this particular point, V out 1 and V out 2, right? Now this V out 1 and output 2, it's an amplifier, right? So the amplifier has got V out 1. Look at this. This is V out 1. Okay, this dotted lines over here is V out 1, and this is V out 2. These two are the signals output for. When there is a CM shift, then there is a clipping of V out 2 occurring. Okay, this is because of the voltage swing. Okay, so this is how the a simple differential circuit is done with. But when you take the two modes of operation, one is differential pair, the other one is common mode pair. Okay, we have drawn this in the last class for the differential pair. Your V in and V in 2 are there. Okay, and I assume my current source ISS. Okay, if my current source is ISS, what would be the value of current that is flowing through this left hand part of the circuit? What would be the value of ISS flowing through the left hand part of the circuit? Ashika, what would be the current which is flowing through the left hand part of the circuit now? Good. And spelled it right, right. Ashika, Ashika, are you
Yes,
there?
sir. Yes, sir.
What would be the output which is flowing through this particular part? Current. You have a total current source of ISS, right?
Yes, sir.
What would be this particular part over here? Over the left hand half of the circuit, what would be the current which is flowing?
No idea, sir.
Okay, I'll move to Mr. Ahatyan. What would be the value of current which is flowing through M1 transistor? Ahatyan, the total current is ISS. So what would be the value of current that is flowing through M1 or the left hand half of the differential circuit? Think, man. Simple.
ID1 plus ID2.
No, my total current source is ISS. Okay, we'll go to one more person and then we'll come back with the answer. Mr. Durai Balaji. Durai, what
Sir,
would be the current which is flowing through the left hand half of the circuit?
IDS.
No, it's not IDS. It is half of ISS. Okay, the total current is ISS. So this half of the circuit will have a current of ISS by 2. Okay, ISS by 2. So the half value of the current would be flowing here. So the remaining half would obviously be flowing through the other end. Okay, this end, the other half will be flowing through. So the total current which is flowing at this particular point is ISS. Okay, so if I assume my R1, RD1, that is this resistance and this resistance to be equal, okay, so the total current of ISS, what is this ISS is put together. If you look at what is the total transistor, if my V in and V in 2 are same, okay, both are getting equal value of biasing, then my output voltage is VDD minus, okay, so output at this particular point. So I'm taking V out 1. So this expression is total voltage is VDD. Okay, V out equal to VDD minus total current over here. Total current is what? IS by 2. Okay, I into R. R is RD1. Okay, if I make my RD equal to uh, RD1 equal to RD2, then it becomes RD. Okay, so the total output voltage V out is given as VDD, the total voltage, minus ISS by 2 into RT. Okay, so this is how you get the expression for this V out. Okay, so all of you know how to write this. So similarly for V2 also, V out 2 also you can write. Okay, so this is the simple differential pair. If you want, you can note it down. I don't think so I'll be able to share this thing. Okay, I think we don't have time, much time, so I'll move ahead to the next portion. We need to do a qualitative analysis. Okay, when you do a qualitative analysis, you have two things to play with. One is with respect to the output voltage. The other one is with respect to the output swing in the current, or output swinging voltage. Okay, so we'll first look at the input output characteristics. So when you look at the input output characteristics, it is basically with respect to common mode. Okay, I'm taking a common mode. The first one was differential mode. Okay, now when you take common mode, I think last class all of you drew the circuit. There are two mode methods in which you represent. One is with respect to a current source. The other one is with respect to the load resistor. Right. So the point of analysis is common mode. So what you do there is you try to interconnect both the input voltages, make it a common V out, and then the other ones are V out 1 and V out 2 output voltages. Right. So this is the configuration of, or the schematic of common mode representation. Either one you can do it. So when you analyze what is the characteristics would be something like this. You have your uh, common mode input, okay, and you have output with respect to current, that is ID1 with respect to M1 transistor, and ID2 with respect to M2 transistors. Okay, so when you plot it, it is obviously going to be above the threshold voltage only the device is going to work. Okay. There is one more important thing which I just want to tell it to you is VPN. Okay, what is VPN is nothing but this point. It's very crucial. This VP point is very crucial because this is the point where the symmetry is split up. Okay, that whole point of voltage setting, that VP point is very significant in analyzing the characteristics, right? So how does the VP with respect to V in vary is something like this. Be a linear steep increase in the voltage after the threshold voltage. Okay. Now when you analyze the characteristics with respect to input output voltage, that is with respect to V out and V in. When you take V out, we have two V outs here. One is V out 1, the other one is V out 2. Okay. But the input here is only one, so it is VCM. So when you plot between VCM and V out 1 and 2, initially you will have the total VDD flowing across this particular terminal. So it will be VDD till the threshold voltage is reached. Once the threshold voltage is reached, then there would be a current which will be flowing from ID into RD and the resistance value. So VDD. So this device will set on. So once the device is set on, they will amplify and send a current. So that current is nothing but your ISS by 2 into RD. This we've seen already. So this ISS by 2 into RD would be the current that is flowing through the output 1. Okay, even output 2 is the same thing. So after that, there is a small decline in the value of VDD in this fashion. Right. So this is the input output characteristics of a common mode transistor. Now we stop it over there as of now. Uh, I just want you to do a small analysis. Please take a piece of paper, okay, and write the expression for V out. Put the heading as differential pair. Please take a piece of your note, open your note, put the heading as differential pair. Put the heading as differential pair, okay, and draw the common. What is that called? Differential pair circuit. Okay, it's not common mode. I repeat once again. Draw the differential mode. Now we are going to analyze the whole system. So draw the differential pair circuit. Two inputs V1, V out. We give two inputs V in and V out. So V in 1, V in 2, common current source ISS, and draw the differential pair circuit. All of you, take your papers fast, notebook, and draw it fast. Okay, I'll give you a minute. Please go ahead. Draw the differential pair circuit fast. Completed? Okay, now I'll ask you one by one. First expression is Mr. Ashwin. What would be the expression for V out, Ashwin? V out 1. Ashwin, Ashwin, what would be the expression for V out 1? You're down the differential pair, right? Tell me the expression for V out 1.
Yes, sir. 1 minute, sir.
Pardon?
1 minute, sir. Drawing the circuit.
In the circuit. Make it fast, man. We don't have much time. Make it fast. Yeah, completed. Yeah, a differential pair circuit. Fast. Okay, how do I draw it? Okay, I'll go to Google Colab. Is that done with? Ashwin? Ashwin?
Yes, sir. Yes, sir.
Yeah. Now tell me what is the expression for V out 1? Expression for
We,
V out 1. V out 1.
sir, VDD minus RD.
Hmm?
V out, sir.
V out 1. Make it clear. V out 1, what would be the expression? I don't know, Jamboard. V out 1, ma.
Sir, ID1 plus ID.
Hmm? Now only I showed the expression also to you. Is it viewing? Okay.
Sir, VDD minus RD ISS by 2.
This is the circuit you drawn. Yes.
Yes, sir. This circuit only, sir.
What is the output you got? V out 1, what would be? You're correct only, man. Tell boldly. That's all.
VDD minus RD ISS by 2.
VDD minus
RD
RD,
1
RD1 into,
ISS by 2.
yeah, before that it is ID into RD. That is fine. I'm
Sir,
asking you
single
for.
output. Sir, the output.
Okay, now V out 2. Balaji, Durai Balaji.
Yes, sir.
Yeah, V out 2. I have shown the answer already.
VDD minus RD2 ID2.
Okay, now if my R1 is equal to R2, Durai, if
Yes,
my
sir.
R1 is equal to RD1 equal to RD2 equal to RD. Okay, now listen carefully, Durai. What would be my V out minus V out 1 minus V out 2? What would be my V out 1 minus V out 2?
RD2.
Hmm. Tell me, right? What would be my V out 1 minus V out 2?
Sir, RD1 minus RD2. ID2.
RD1 minus.
Sir, ID1 minus ID2.
Okay, fine. Good. All of you write it down. Yes. What is my collab? Yeah. All of you write what is V out 1 minus V out 2. I will. Okay. Now that is done with as of now. Now you have to
Sir.
find. Yes. Somebody has
Yes, sir.
interrupted. Tell me. Yeah. Now take down this. Assume the circuit is symmetry. Assume the circuit is symmetry. M1 and M2 are in saturation. Assume the circuit is symmetry. M1 and M2 are in saturation and lambda equal to 0. And lambda is equal to 0. And lambda is equal to 0. Then V in 1 minus V in 2 equal to V in 1 minus V in 2 equal to VGS1 minus VGS2. V in 1 minus V in 2 is equal to VD V in 1 minus V in 2. Okay. All of you have completed till here? Can I have a response, please?
Yes, sir.
Below that, take down, ma. For a square law device, for a square law device, for a square law device, V in 1 minus V in 2 is given as all of you know this expression, right? How do you get it? Also, you know, root of 2 ID1 by mu n COX WL minus root of 2 ID2 mu n COX W by L. So we'll continue the next in the next class.